This is the video where I teach you everything you need to know about carbon NMR. I'll give you the basics and just the cheat code on learning these basic things before you go into that exam. We've learned a lot about hydrogen NMR. And in the hydrogen NMR, we are looking for the hydrogen atoms. So what are we looking for in a carbon NMR? You guessed it, the carbon atoms. Now carbon, we said earlier that you have a little nucleus. Inside of the nucleus of these atoms, you have a little magnet. But not every nucleus gives you a magnet. Only those with an odd number of protons or an odd number of neutrons. Now carbon, normal carbon, weighs 12 and it's number 6 on the periodic table. That means it has 6 protons. It's not a nucleus because of that. And it has 6 neutrons. That's even. That's not going to be a magnet because of that in the nucleus. So carbon, normal carbon that weighs 12 is invisible in the NMR. You can't see it. But here's the good news. Every once in a while, a carbon, which is number 6, 6 protons, has 1 extra neutron, and it weighs 13. And with 7 neutrons, that is going to be spin active. That means it has a nuclear spin and it's a magnet. And we can see carbon that weighs 13 in the NMR. But not all carbon weighs 13. Remember, most of it weighs 12. Only about 1% of all carbon weighs 13. So in any molecule, you have a 1% chance that the carbon atom might be active and you can see it. Okay, now that we know that only about 1% of our carbons will be seen in the NMR, and the magnet's not all that sensitive. So you have to run a bunch of scans for this one in order to start to see these carbons. So this NMR takes longer to run, and you have to be a little more careful and have maybe more sample in order to start to see these carbons. All right, so carbons. We're looking at carbons now and not hydrogens. Now carbon atoms, their NMR scale, so it goes not from 0 to 10, but from 0 to about 200. So 150, 200, 50, and 0. Again, the unit is parts per million for the carbon NMR. All right, now here's the cheat code. These are the 4 regions. I've narrowed it down to 4 regions that you should study. 0 for us is, again, the molecule TMS. We use that to zero the NMR. Now, from 0 to 50, these are my regular carbon atoms. Those are carbons that are on regular hydrocarbons, not next to anything special. From 50 to 100, these are carbons next to something special. So that's a carbon next to an oxygen, a nitrogen, a chlorine, a bromine. If you're next door to a carbonyl, you're kind of somewhere right around 50 in the middle. Now, 0 to 150. So I just have 0 to 50, 50 to 100. 100 to 150 are carbons that are on double bonds. That might be a regular carbon-carbon double bond, or that might be a phenyl ring double bond. But these are carbons that are in a double bond thing. And finally, above 150 are carbons that are carbonyl carbons. Those are the 4 regions. That's the cheat code. Your regular carbons, next to something special, double bonds, carbonyls. And if you get those 4 things down, you can figure out most everything else. Learn those 4 regions and get them down pat. Right now, learn them. Don't forget them. Learn them right now. Regular carbons, next to something special, part of a double bond or a phenyl ring or a carbonyl. That's it. That's how you start with carbon NMR. The other thing about carbon NMRs, I guess you should know, is that the integral, how many carbons it represents, you have to be very careful with carbon NMR. We don't usually look at the integrals. Instead, carbons that have a lot of hydrogens on them, like methyls or CH2s, those carbons tend to be pretty big in my carbon NMR. Ones that have 1 hydrogen on them, they tend to be a smaller peak, and a carbon with no hydrogens tend to be fairly tiny. So you can't compare one carbon to the other. So yeah, this one's twice as big as that one. There must be two of them and one of these, because some of them end up being smaller, ones without hydrogens on them or with only one hydrogen. So we don't usually integrate. The other thing is, because carbon NMR is not very sensitive and you don't have a lot of carbon atoms in them, what usually happens is your NMR looks like a bunch of noise. You have a bunch of peaks when you first start to run it. And this is just random stray noise that you get. And then if you run several scans where you get a random noise peak, the next time you run it, maybe you don't get that random noise peak. So your noise gets smaller and smaller and smaller and smaller as you start to run a bunch of scans. But if you have a carbon peak, let's say this is really a carbon peak, and you start to add it together, and every time you run that carbon peak, it says, no, that's a real peak, that's a real peak, that's a real peak. So eventually what happens is your noise gets smaller and smaller. Here's my noise. And your peak starts to peak out a little bit. And maybe you get another one that just starts to grow out a little bit farther. So you're like, is that a peak or not? I'm not quite sure. So maybe you run a whole bunch of more scans and the noise starts to disappear. And if that peak is a real peak, it'll always show up and you'll see it. So we have to run a bunch of scans to get our carbons to start to peak out. The other thing about that is if I'm looking at a carbon atom with a hydrogen on it, this is a little tiny magnet on top of this magnet. So this carbon, if it has one hydrogen, if I don't do anything about it, it'll split into a doublet. And you'll get two peaks for that carbon atom. The problem is if you have one big peak, right, it's this big, but you split it into a doublet, you get two half-size peaks. And pretty soon it gets into the noise, and that's a problem for me. So normally what we do is we send a whole bunch of radio waves that take this magnet, which is either up or down, and we flip it back and forth real fast and we average it out. That way this carbon isn't either up or down to a doublet. It ends up being one peak and it starts to double the size of it and it peaks out of the spectrum a little faster. Okay, what that means for us is we don't usually do spin splitting, and we don't usually look at the integral. All you have to know is the four regions of the carbon NMR spectrum where they show up. So here's a compound for you. Let's take a double bonded carbon. There's two hydrogens on that one hydrogen there. Let's pick a carbonyl and an ethyl. So we have, let's go ahead and label them. 1, 2, 3, 4, 5 types of carbons. A, B, C, D, and E. So there's 5 different types of carbons. I expect to see 5 different peaks here. And here's what you see. You get one peak out here, close to 200. That's in the carbonyl region. That is peak C, carbon C, the one that's the carbonyl. You end up getting a couple of peaks here. One here, and maybe one about here. Which ones are these between 100 and 150? Those are our double bonded carbons, A and B. A is a little bit bigger because it has more hydrogens on it than B is. And then C and D, these regular ones down here, they end up looking something like, so D and E. 2 regular carbons between 0 and 50. So in a carbon NMR, what you see is 1, 2, 3, 4, 5 peaks. That tells me I have 5 different types of carbon atoms. 1, 2, 3, 4, 5. 2 of them are regular carbon atoms between 0 and 50. 2 of them are double bonded carbon atoms. So I have a carbon-carbon double bond. And 1 of them is a carbonyl. It's between 150 and 200. So it tells me what types of carbons, how many I have, and something about their chemical environment. I don't integrate this. I don't have twice as many of this one as I do of this one, even though that peak's twice as big. All I know is how many types I have and what types of carbons they have, or what the chemical environments are. That's all I know. So I don't integrate, and I don't look at splitting. I just look at carbon atom. This is a carbon NMR. A carbon NMR. That's it. So learn your 4 regions. 0 to 50 regular. 50 to 100 next to something special. 100 to 150 on a double bond. And above 150, a carbon that's on a carbonyl. I hope that video was helpful for you. That's the basic understanding of carbon NMR. We just look at these single peaks, we count how many we have, and we just learn those 4 regions.